For this video, I want to go through some examples of questions in past papers. So in the first question, they say that the chemical equation for this reaction can be represented as shown. So our first molecule has a carbon-carbon double bond, and then we add a chlorine molecule, and this will give us a halogenoalkane, meaning that we have chloride bonded to a single bonded carbon-carbon. They then say that the energy change for this reaction is negative 180 kilojoules per mole. Now we need to use the bond energies in the table to calculate the bond energy of a carbon-chloride bond in kilojoules per mole. We can then see our table with our different bond energies, and then we're going to start. So the first thing that we're going to do is we're going to calculate the energy needed to break the bonds. So we can see that we need 4 carbon-hydrogen bonds. We also need to break 1 carbon-carbon double bond, and then of course we need to break 1 chloride-chloride bond. So we can see here in our table that a carbon-hydrogen bond is 410 kilojoules per mole. Then my carbon-carbon bond here in my table is 610 kilojoules per mole. And then my chloride-chloride bond is 240 kilojoules per mole. So I'm going to add all of these together, and this will give me 2,490 kilojoules per mole of energy that would be needed to break the bonds. So our second step will then be to calculate the amount of energy that's given off by the bonds being formed. So on the right hand side of my equation, I can see that I need 4 carbon-hydrogen bonds. I also need 2 carbon-chloride bonds, and I'm going to form 1 carbon-carbon single bond. So I'm going to go back to my table, and I'm going to go have a look and see that my carbon-hydrogen bond has an energy value of 410 kilojoules per mole. My carbon-chloride bond has an energy value of, we don't have an energy value here because that's the one that we need to work out. So we're just going to rewrite it as 2 carbon-chloride. And then my carbon-carbon bond has an energy value of 350 kilojoules per mole. So I'm going to multiply my 4 in with the 410 and then add 350, and that will give me 1,990. And I'm going to rewrite again my 2 carbon-chloride bonds. So we can't work out the carbon-chloride bond just yet from what I have. So we're going to move to the next and final step. So I know that my change in enthalpy, or my delta H, is equal to the amount of energy needed to break my bonds minus the amount of energy produced by forming the bonds. My change in enthalpy value I can get from my question as negative 180 kilojoules per mole. And then my bonds broken, I have worked it out as 2,490 kilojoules per mole. And then my bonds formed, I'm going to put this in square brackets to remember to multiply in my negative. So this is going to be my 1,990 plus 2 carbon-chloride bonds. I can then multiply in my negative into my square bracket. So I'll get negative 180 is equal to 2,490 minus 1,990 minus my 2 carbon-chloride bonds. I can then minus my 1,990 from my 2,490, and this will give me a negative 180 is equal to 500 minus my 2 carbon-chloride bonds, and then I can take over my 500, and this will become a negative 180 minus 500 is equal to negative 2 carbon-chloride bonds. This will give me negative 680 is equal to the negative of my 2 carbon-chloride bonds. I'll then divide both sides by -2 and I'll get my value of my carbon chloride bond as 340 kilojoules per mole. This means that 340 kilojoules per mole is given off when a carbon chloride bond forms in my reaction. Let's have a look at the next question. So they say that ethene is an alkene which reacts with bromine as shown in the equation. So we can see that alkene C2H4 plus bromine will give us our alkane or halogenoalkane, which is C2H4Br2. Now part of the energy profile diagram of the reaction is shown. So they show us the graph of energy over the progress of the reaction, and they do give us our reactants as a high energy value. They then say that the reaction is exothermic, and they ask you to complete the energy profile diagram for the reaction. So the first thing that we need to include is the position of the products. Now we know that this reaction is exothermic, so our products would have a lower energy value than our reactants. So we'll put that line right here. Now we have to remember to also write down our products on the line. So on top of the line, we'll write C2H4Br. Okay, so the second thing that we need to include is an arrow to show the activation energy labeled as A. Now remember, our activation energy is the amount of energy needed by the reactants to initiate the reaction. So we're going to complete the graph by continuing our line from our reactants upwards, creating a hump, and then downwards to our products. Now from the line of our reactants to the maximum point of our graph would be our activation energy. So we can draw a line showing upwards, so our arrow will show upwards and we'll label it as A. Lastly, we need to include an arrow to show the energy change of the reaction. Now, the energy change of a reaction is the difference between the energy of the reactants and the energy of our products. We also know that this reaction is exothermic, so the change in our energy will be negative. So our arrow would point downwards. So we'll draw an arrow from the level of our reactants all the way down to the level of our products. In our next question, they said that this chemical equation for the reaction can be represented as shown. So they gave us ethene, which is a double bonded carbon organic molecule, plus bromine gives us bromoethane. They then give us some bond energies, so we can see the different bond energies for each bond, and then they ask us to use the bond energies in the table to calculate the energy change in this reaction. So the first thing that we're going to do is we're going to calculate the amount of energy needed to break the bonds. So we can see that we need to break 1, 2, 3, 4 carbon-hydrogen bonds. We also need to break a carbon-carbon double bond. And lastly, we need to break a bromide-bromide bond. So if we go and look at our little table here, a carbon-hydrogen bond is equal to 410 kilojoules per mole. So we're going to say 4 times 410 plus a carbon-carbon double bond will be 610 kilojoules per mole. And lastly, my bromide-bromide bond would be 190 kilojoules per mole. Now, if I add all this up, I'll get a total energy needed to break all of these bonds as 2,440 kilojoules per mole. So this is the amount of energy needed to break all of the bonds. Now, the second step is to calculate the amount of energy that's being released from the bonds being formed on the right side of my reaction. Now, I can see from the right side of my reaction that there is 1, 2 carbon-bromide bonds. There's also 1, 2, 3, 4 carbon-hydrogen bonds and 1 carbon-carbon bond. Now, if I go and look on my little table, a carbon-bromide bond is equal to 290 kilojoules per mole. So I'm going to multiply that by 2. And then my carbon-hydrogen bond is 410 kilojoules per mole. I'm going to multiply that by 4. And then lastly, my carbon-carbon single bond is equal to 350 kilojoules per mole. Now remember, it's very important here to make sure that you understand what type of bond is in the reaction. Is it single bond or is it double bond? Now if I add all of these together, I get a total of 2,570 kilojoules per mole of energy that's being released when the bond's formed. So my last step is to calculate the enthalpy change. So I remember that my enthalpy change is equal to the bonds being broken minus the bonds being formed. Now the total energy needed to break my bonds was 2,440 kilojoules per mole, minus the total energy released from my bonds being formed was 2,570 kilojoules per mole. Now if I work out this difference, I get a difference of negative 130 kilojoules per mole. Now remember, as a side note, this little negative here means that my reaction is exothermic. Okay, let's do another one. So in this question, they say that the energy profile diagram of this reaction is shown. So they give us a graph which shows the amount of energy over the progress of the reaction. We can see our reactant's energy quite high, and then there's an increase in energy, a decrease in energy, and then our product's energy below it. They then ask us to name the energy change labeled A. Now, if we go to A, we can see that A is from our reactants increasing. Okay, so this would be the amount of energy that's needed to initiate the reaction, or otherwise known as the activation energy. The second question asks to name the energy change labeled B. Now B, we can see, is going downwards from about below A. So we can see that it's the difference between the energy of our reactants and the energy of our products. So we can say that this is the energy change of the reaction. Lastly, they ask us to state how the energy profile diagram shows that this is an exothermic reaction. So if we go back to our diagram, we can see that the amount of energy for our reactants are more than the amount of energy for our products. So we know that this is an exothermic reaction because the energy of our products is lower than the energy of our reactants, meaning that the system loses energy. In the next question, they say that the equation for the reaction can be represented as shown. So they gave us an ethane plus chlorine, which would give us chloroethane and hydrochloric acid. They then give us a table with all the bond energies and ask us to use the bond energies in the table to calculate the energy change in the reaction. So just like before, we're going to start by working out the amount of energy needed to break the bonds of our ethane and our chlorine molecule. We can see on our diagram that there's 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds, and also 1 carbon-carbon bond and 1 chloride-chloride bond that would need to be broken. I can then go look on my table. My carbon-hydrogen bond is equal to 410 kilojoules per mole, so I'll have to multiply that by 6. Then my carbon-carbon bond is 350 kilojoules per mole, and my chloride-chloride bond is 240 kilojoules per mole. When I add all of this together, I get a total of 3,050 kilojoules per mole of energy that's going to be needed to break all of these bonds. Now my second step is to calculate the amount of energy released when I form the bonds. So I can see that there's 1, 2, 3, 4, 5 carbon-hydrogen bonds that will form, and 1 carbon-chloride bond, as well as 1 carbon-carbon bond and 1 hydrogen-chloride bond. So now I go back to my table. My carbon-hydrogen bond has a value of 410 kilojoules per mole, which I would have to multiply by 5. My carbon-chloride bond has a value of 340 kilojoules per mole. My carbon-carbon bond will have 350 kilojoules per mole, and my hydrogen-chloride bond would have 430 kilojoules per mole. So when I add all of this up, I would get a total of 3,150 kilojoules per mole of energy that is released when these bonds are formed. I then have to work out my energy change, and this is my enthalpy change. And I work it out by saying the bonds broken minus the bonds formed. Bonds broken was equal to 3,050 kilojoules per mole. My bonds formed was 3,150 kilojoules per mole, and the difference between these two is negative 100 kilojoules per mole. Another reminder, the little negative in front of this value would refer to the reaction being exothermic and releasing energy overall. Hopefully by now you realized that the bond energies can be used for either forming bonds or breaking bonds, and that there's no difference between the bond energy to, for instance, break a carbon-carbon bond and to form a carbon-carbon bond. Okay, let's move on. So in this question, they say that chloroethene, which is a double bonded hydrocarbon, can be manufactured from 1,2-dichloroethane. Now the equation can be represented as shown. 1,2-dichloroethane, giving us chloroethene and hydrochloric acid. They then say that some bond energies are given in a table, and we need to use these bond energies in the table to calculate the energy change in kilojoules per mole of the reaction. Okay, so we know how it goes by now. First, we're going to calculate the bonds broken. So this would mean that there's 4 carbon-hydrogen bonds that need to be broken, as well as 2 carbon-chloride bonds that need to be broken, and 1 carbon-carbon bond that needs to be broken. So if I go to my table, I can see a carbon-hydrogen bond has a value of 410 kilojoules per mole, so I'll have to multiply this by 4. My carbon-chloride bond has a value of 340 kilojoules per mole, and I'll have to multiply this by 2. And then my carbon-carbon bond has a value of 350. If I add all of this together, I get a total of 2,670 kilojoules per mole. So in my second step, I'm going to calculate the amount of energy released from the bonds being formed. So first, I can see that there's 3 carbon-hydrogen bonds, as well as 1 carbon-chloride bond, 1 carbon-carbon double bond, and 1 hydrogen chloride bond. I'm then going to move back to my table and see that my carbon-hydrogen bond has a value of 410 kilojoules per mole, which I'll be multiplying with 3. My carbon-chloride bond has a value of 340 kilojoules per mole. My carbon-carbon double bond has a value of 610 kilojoules per mole. And my hydrogen chloride bond has a value of 430 kilojoules per mole. So when I add all of this together, I get a total of 2,610 kilojoules per mole. Lastly, I'm going to work out the enthalpy change. So I'm going to take the energies needed to break my bonds minus the energy released when my bonds are formed. Now this would be 2,670 minus 2,610, and it will give me a difference of 60 kilojoules per mole. Now this value has a positive, meaning that it's an endothermic reaction and energy overall is being absorbed by the reaction. Now my second question, they asked to deduce whether the energy change for this reaction is ectothermic or endothermic, and we need to give an answer. Now we already know that it's endothermic, and our reason for this is that the change in enthalpy is positive for this reaction, and more energy is needed to break the bonds than being released by forming the new bonds. Next, we have a question that says that figure 5.1 shows an incomplete reaction pathway diagram for the forward reaction. So we can see that they give us carbon chloride, or otherwise carbon tetrachloride, plus water gives us carbon dioxide and hydrochloric acid. In my graph, I can see that my energy of my reactants is quite high. The energy then increases, decreases, and the energy of my products is then very low. They then say on figure 5.1, insert the formula of the reactants and products. So my reactants would be carbon tetrachloride plus 2 water, and I will add this to the first line that I see on my energy diagram. Then my products would be carbon dioxide and hydrochloric acid, and I'd add this on the second flat line of my diagram. Next, they ask us to draw an arrow labeled EA to show the activation energy. So this arrow will be from the level of my reactants up to the maximum level of my energy. Then lastly, they ask us to draw an arrow labeled delta H to show the transfer of energy in the reaction. So remember, this is an exothermic reaction because it releases energy, so my arrow needs to point downwards. My delta H will be the energy change. So my arrow will be from the level of my reactants downwards to the level of my products. The second question then asks to define the term activation energy. Activation energy can be defined as the minimum amount of energy that's needed by the colliding particles to initiate the reaction. And then lastly, they ask us to state one way in which the activation energy of a reaction can be changed. Now, the activation energy can be decreased by using a catalyst. Now, remember, a catalyst is able to decrease the activation energy by producing alternative pathways for the reaction to take. Okay, so let's have a look at the last question for today. So in this question, they say that the equation for the reaction between tetrachloromethane gas and steam can be represented as shown in figure 5.2. Now in figure 5.2, we can see tetrachloromethane plus 2 water molecules will give us 1 carbon dioxide molecule plus 4 hydrochloric acid molecules. They also show in this figure the change in enthalpy, which is negative 130 kilojoules per mole. They then give us table 5.1, which shows some of our bond energies. They then ask us to use the bond energies in the table and the change in enthalpy value for the reaction to calculate the hydrogen chloride bond energy. So we're going to start this question the same as we start all the other questions, by calculating the amount of energy needed to break the bonds. So we know that there is 4 carbon chloride bonds, as well as 4 hydrogen oxygen bonds that need to be broken. Now on my table, my carbon chloride bond has an energy value of 340 kilojoules per mole, and my hydrogen oxygen bond has a value of 460 kilojoules per mole. Now when I add these two together, I get a total of 3,200 kilojoules per mole. Next, I'm going to calculate the amount of energy released when my bonds are formed in my reaction. So I can see that there's 2 carbon-oxygen double bonds, as well as 4 hydrogen chloride bonds that need to be formed. So I'm going back to my table to see that a carbon-oxygen double bond is equal to 805 kilojoules per mole. And my hydrogen chloride bond is the bond that I need to calculate. So I'm just going to write it down as I have it. I'm then going to multiply my 805 by 2 to get 1,610 plus my 4 hydrogen chloride bonds. I'm then going to move on to the next part of the question where I work out my enthalpy change, which would be equal to the energy needed to break my bonds minus the energy released from forming my bonds. Now my change in enthalpy is equal to negative 130 kilojoules per mole. This will be equal to my bonds broken, which is 3,200 kilojoules per mole, minus my bonds formed. So that would be minus 1,610 plus 4 hydrochloric acid bonds. Now I like to put this in brackets because then I know to multiply in my negative, which would give me negative 130 equals to 3,200 minus 1,610 minus my 4 hydrochloric acid bonds. I then can minus the 3,200 minus the 1,610, which would give me minus 130 equals to 1,590 minus my 4 hydrochloric acid bonds. I can then take over my 1,590, which would give me minus 130 minus 1,590 would be then equal to my negative 4 hydrochloric acid bonds. This will then give me negative 1,720, which is equal to my negative 4 hydrochloric acid bonds. I then divide by negative 4 on both sides to get my hydrochloric acid bonds as a total of 430 kilojoules per mole.